Welcome back. This video begins our study of how things fail due to fatigue failure. So we've looked at static failure and we've looked at fatigue failure, and we're going to look at fatigue failure. So first of all, we want to kind of differentiate what is the difference between these two. So static failure assumes that there's a gradual application of the load. That means that there is time for the strain to exist. So if you think about any lab experience you've had where you put a test specimen in the machine, stretches it and tries to make it break, what happens is that that load is very slowly applied. And that slow application is important because it allows the atoms to move around and it allows that deformation to actually occur. So a different, and that ends up leading us to see yielding, that is the plastic deformation. If the load is applied quickly and there's no time for that strain to build up in the part, then we can see brittle failure. Another way that we end up seeing brittle failure, or ways that a crack starts growing in a part, is due to a cyclic loading. So the difference between what we've been looking at and what we're going to look at is static failure is looking at one instance of time and seeing if it will break, and dynamic failure, or fatigue failure, is looking over its period of time and evaluating whether it will break. So another way to look at this difference is that in static loading, we have some maximum stress that our part can experience, and in dynamic loading, we look at how the loads or the stress varies over time. So there are several different ways that dynamic loads can change over time. So we could imagine a load which fluctuates between some maximum and minimum and goes to 0, where this is our stress and this is our time t. We could imagine putting our part under some loading and then it's not used, and then at some other time it's put under some loading, so on and so forth. Or it may just fluctuate between any two values. So we'll talk about these in particular to evaluate how we define what type of loading it is, because some cases will be easier to deal with than others. So the purpose of this video is to give a basic introduction to fatigue failure analysis. So what is fatigue failure? So fatigue failure is failure that happens over time, and it's caused by crack propagation. That is, over time, a crack begins to form in a part and then begins to grow. So because we're talking about crack propagation, that should key you into realizing we're going to need to look at stress concentrations. Stress concentrations are how we cared about and how we modified the stress values to account for the fact that there might be microscopic cracks in the part. The other thing to be careful about with fatigue failure, and why we care about it, is because it is crack propagation, it looks like brittle failure. That means it is it can be a sudden and quick and total fracture. It happens well below the ultimate strength. And it usually occurs after either thousands or millions of cycles. So just like static failure analysis, we have theories of how things break. And the reason we have theories for fatigue failure is that there is no repeatable scientific law that governs the probabilistic behavior of how cracks grow. So when we get down to the very minute level and we're looking at whether or not a crack will form at a particular location, the arrangement of those atoms and the probabilistic nature of our universe mean that there's no way to deterministically and absolutely say, yes, a failure will occur here. All that we will do is say, based on high probabilities and over a certain period of time where those probabilities exist, we can say that there is a likelihood of failure. So we have what are called fatigue failure theories. And fatigue failure theories basically sum up to the same thing of static failure, but we create and we introduce a new term. And that is when the loading is such that the stress is greater than the endurance strength. So we need a new term here, the endurance strength. When the stress of fatigue loading is greater than the endurance strength, a part will fail within a period of time. So we'll expand upon this and provide some real numbers and details in following videos. But for now, what we want to really understand is, given that we can calculate the stress, and given that we can determine, based on material properties and some loading and geometry, what the endurance strength of our part ought to be, what is this given time for which a part will fail, and are we acceptable with that? So if a part will fail in 1,000 cycles, is that going to be significant to us? Or if it doesn't fail for 1,000,000 cycles, perhaps we don't care about it. So our goal is to find and estimate the number of cycles, the life in terms of number of cycles. So the number of cycles is the cycles of loading, and we use a term N, capital N, and it is based on the conditions. So our general fatigue process is going to be basically the same, and all we're going to do is add to it. So I'm going to outline the process now, and we'll do it many, many times. So the process begins with finding an approximation for the endurance strength. This value we're going to call SE prime. Second, we need to modify that approximate endurance strength to be a more accurate or a true endurance strength. The third step of our process is we're going to find out what sort of stress concentrations exist that might make a fatigue fracture likely. So these are the fatigue stress concentration factors. Step 4 of this process is to apply our fatigue factors, stress factors, to the nominal stress that we can calculate based on the loading to calculate an enhanced version or a higher version of stress that accounts for how likely a fracture or a crack is to grow at that location. Step 5 of our fatigue analysis is where we're going to actually see if this modified stress accounting for concentration factors is greater than our modified evaluated endurance strength. This gives us our value of our fatigue factor of safety. Finally, our sixth step and final step is to make sure that even if our stress is below the endurance strength, it's possible that that endurance strength can be higher than the yield strength. So even though our fatigue approach will say it will last so many cycles, in fact, when we look at it, it won't last the first cycle because the stress is greater than the yield strength. So the last step is to check for yielding. So this is the basic process, and if you were to write a problem-solving algorithm, we're going to end up doing this over and over again. And the things that will change are how we determine the endurance strength, how we determine what the stress concentration factors are, and what our values of stress R for applying these things. So we're going to use this process over and over again. Finally, I'd like to take a look at cyclic loading. Cyclic loading is what's going to be causing our fatigue failure analysis. So what we need to do is characterize this type of loading, because some types of stress are going to be much easier for us to understand, and some are going to require a slightly more complicated approach. So there are, in general, 3 types of cyclic loading. The first one, which is what we'll start with, is the easiest. It's called fully reversed. So if we draw a diagram that shows our value of stress, and this could be shear stress, it could be bending stress, it doesn't matter. I'm just going to use a value of sigma to represent stress. And we plot that over time. Fully reversed means that at some point the stress reaches a maximum, and at another point in time the stress reaches a minimum. And it cycles between those maximums and minimums. And if these maximums and minimums, the magnitude of them are the same, and the mean is 0, we call this fully reversed. So there are 2 values that are going to be important to us. One is the mean stress, sigma m. This is the mean stress. And the other is sigma a. This is the amplitude stress. So the mean stress, or the amplitude stress, are what we use to define our cyclic loading. So the mean stress, for fully reversed, as you can guess, is the mean of 0. So fully reversed means that the mean is 0. Sigma m equals 0. It also means that sigma a, the amplitude stress, is the same thing as the magnitude of the maximum. Or the magnitude of the minimum. It really doesn't matter which one you use. It also doesn't matter how we get to those 2 points. So we could have a graph that looked like this, where we've got some triangular loading, or we could have a square wave. It really doesn't matter how we get to that loading, only that we have a mean stress of 0 and an amplitude that's equal to the maximum or minimum. If the mean stress is 0, we're in the situation 1 fully reversed. So if the mean stress is not 0, then we're in the type of situation where we've got a fluctuating load. So the fluctuating load, again drawing the same stress over time curve, just fluctuates between 2 values. So we could have some maximum, sigma max, and some minimum, sigma min, and it will the stress values will fluctuate between the 2. So for a fluctuating load, sigma m, the mean stress, recall, is not equal to 0. It's equal to something. The amplitude stress, sigma a, is equal to the absolute value of the maximum minus the minimum over 2. So recall the amplitude is just how much above the mean we are. So if we've got our mean stress, sigma mean, the amplitude is how much above or below we are from that mean. So we can use half the distance between the maximum and the minimum to get us there, or the distance between the maximum and the mean. The mean, of course, is just the average. So the sigma mean equals sigma max plus sigma min over 2. We don't want to use the absolute values here because it'll become important to us whether the mean is always in compression or if over on average the stress is in tension. So there's a couple special cases of the fluctuating load. One that we see quite often is what's called the release load. This is a special type of fluctuating load. That means nothing really happens to our part, and then all of a sudden at some point it gets loaded up for a while and then nothing happens. So think about one tooth on a gear as it's going around connecting with another tooth. First it transmits the force from one tooth to the other tooth, and then it releases that force, and then as it goes its way around the rest of the circle, nothing really happens to it. So this is a special case of release load. Finally, our third type of loading that we're going to look at is combined loading. So before I noticed I implied that basically we only have one value of stress acting on this part. I just used a sigma. I could have just used a shear stress. But the implication there is that there's only one value of stress acting on our part. In reality, for most parts, there's actually multiple sources of loads, and they can fluctuate over time. And these multiple loads may all have their own sigma m's and sigma a's. Or for torsion, we'd have tau mean or tau a. So we're going to have to come up with an approach that puts all these together in a way that makes sense. So we could have a situation where we've got, over the same period of time, this will be our axial load over time. This can be our bending load. That'll also produce a normal stress that we care about. And we could have some torsion over time, causing some shear stress that we care about over time. So if we think about a shaft carrying a couple gears, for example, if they are helical gears, while that shaft is spinning, so it starts spinning up, and that axial force of those gears pushing on each other creates some constant over the entire time frame. However, if we look at a point on that shaft, at one point the bending would be maximum, and then as that shaft rotates down, that point on the shaft is now in compression and have some maximum, and it would fluctuate between the maximum and the minimum. Same thing would happen for our torsion diagram. So as the shaft with the gear starts spinning up, the torque increases, and as long as that shaft is spinning, the torque should be basically constant. So we've got 3 different time periods and 3 different types of cyclic loading, and we'll want to be able to compare what is the sigma m due to axial stress and the sigma a due to axial. What is the sigma m due to bending stress? What is the sigma a due to bending stress? And what is the shear stress, the mean shear stress from torsion, and the amplitude shear stress from torsion? And what we end up going to be using is von Mises stresses to combine all those together. That's why von Mises was and the distortion energy approach was so important to us before. All right, well, that will about do it, and what we've done so far is we've wrapped up what fatigue failure means and the types of cyclic loading that we're going to have. And to begin explaining fatigue loading, we're really going to focus on the fully reversed case, because that will help us identify and apply the modified Goodman fatigue failure equations and understand fatigue failure a bit better. That'll about do it for now.